On Lagrangian reachability, and the talk will be given by Jacek Cyranka.
Thank you for your introduction. So I'm going to present a presentation about our paper on Lagrangian reachability. It's a joint work with Arif Islam, Greg Byrne, Paul Jones, Scott Smoka, and Radu Grosu. So the problem we deal with is about ensuring stability of emerging systems like cyber physical systems and controlled biological systems. And usually these systems are modeled by continuous dynamical systems or called hybrid dynamical systems, which are discrete and continuous at the same time. So in our work, we deal with, for the moment, we deal with continuous dynamical systems. We study nonlinear time variant ODEs. So solutions, it's well known that solutions are smooth trajectories in Rn. Unlike linear systems, the solutions are not in closed form, so there's not nice formula for solutions in general. So the only thing that we can do is to bound the solution. Because we don't know the formula for the solution, so we can bound it to ensure safety, right? So our goal is to compute so-called rich tube. So we have like initial set of states, and our goal is to bound the set of solutions which starts within this set. Okay, and this set is infinite, so we want to bound all solutions which start somewhere inside this set, which in our case is a ball. And it can be done, I mean, it's not so hard to find any rich tube. We can take a really large set, which will and then prove that it contains all solutions, but it's not what you are interested, because in typical applications there's like unsafe region or so-called guard region, and in order to avoid false positives, we want this set to be as tight, this rich tube to be as tight as possible. Right. Because as you see on this picture, too big set will result in false positives. Okay, so in this dark green we see the true trajectories, and this light green is our overestimate, and in fact this overestimate intersects unsafe region, but in truth all of the trajectories, they are safe. Okay. So we are interested in finding this as tight as possible rich tubes in order to avoid false positives. So there's a bunch of existing methods, existing software which deals with this problem. So these methods fall into three paradigms. First, I would call is Taylor expansion in time and variational expansion in space. There is CAPD library. There is V-node library. The second paradigm I would call Taylor expansion in time and space. It's called Taylor model, and there is cos infinity, which is not open source, and there is FlowStar. And there is third paradigm, which is so-called, I would call, bloating factor discrepancy function base. It comes from a group at Urbana-Champaign. All right. So our approach is kind of complementary. So we explore possibility of computation of the ridge tube using a well-known method of Lagrangian coordinates, and we explore if there are some advantages of doing so. So Lagrangian coordinates are well known and widely used in material science. So this is the classical picture from Wikipedia. So there is some continuous body which gets deformed, okay? And we start with these coordinates in undeformed configuration are called Euclidean coordinates, and then after deformation we have Lagrangian coordinates, okay? And this deformation in particular can happen in time. There are various interpretations. It can happen in time or under some force. In our case, we are going to apply this technique for a solution set of ODEs. Okay, so our goal is to compute a given initial set of states, compute sequence of states, time-stamped, sequence of sets of states which are time-stamped, and they satisfy that ridge set is contained in those sets, okay? For the moment, we deal with so-called discrete ridge tube, so times are, so we compute this set of states at given times, okay? And then I will comment how to extend it for continuous time. So this is the pictorial representation of our algorithm. So we represent sets using balls. And ball can be in, as you see on the left, is a ball in Euclidean space. So I'm presenting this in two-dimensional phase space. It can be any dimensional, of course. So at given time, the enclosure for the set of states is given by a ball. It can be in Euclidean ball or a ball in any metric space, any weighted metric space. And a ball in weighted metric space is going to look like a tilted ellipsoidal set, like you see on this right. And the method works like I will explain more or less. So you can read details in our paper. So there's dynamics happening in order to bound the set of states which initiate within this ball. We are going to compute so-called stretching factor, which will tell us how much this ball gets stretched. And moreover, we are going to compute norm, okay? Because this norm can change when we move from time to time. And this is, we do it because we are interested in finding as tight as possible ridge tube. So maybe like Euclidean ball is not good. It's maybe too wide. I mean, it's maybe too big overestimation. So we would like to find maybe like ellipsoid which will bound the ridge set better. And we do it by finding appropriate norm. And then, yeah, the stretching factor will tell us how much the radius will change. So this is, in a nutshell, how this works. And of course, we have to, compute how the center, because this ball will propagate in time, so we need to propagate the center. And then compute the radius. And yeah, that's it. So these are the ingredients of our algorithm. So we need, in order to be able to do this, first of all, we need to compute gradient of solution flows, which are called sensitivity matrix in the literature. And you need to be overestimate. So for the moment, we use CAPD library in order to compute this. It can be done independently, but for the moment, our code is like a prototype, so we don't have a tool yet. Having this sensitivity matrix, we can compute so-called Cauchy-Green deformation tensor. And then, having this, we compute positive definite matrix, symmetric matrix, which will define a norm in the next time step. So I'm presenting how to do one time step in our algorithm. And then this norm is such that stretching factor is minimized, okay? So the stretching factor is like square root of maximal eigenvalue of deformation tensor, and it tells us how much the radius change, okay, from here to here. And this norm is such that this stretching factor is kind of minimized with some resolution, of course, because we have whole set of solutions, so we cannot minimize over, I mean, we could, but I mean, it's kind of hard problem to minimize over set of all trajectories, so we just pick one of these gradients contain, I mean, for one of those trajectories. So once we have norm and the overestimate for deformation tensor, okay, so look, I mean, we need to overestimate for all trajectories because we're interested in overestimation for the solution set. So we need to overestimate kind of this deformation tensor for all trajectories. So once we have this overestimate and the norm, we can compute upper bound for stretching factor, which is just square root of maximal eigenvalue of this interval matrix. We use external tools to compute. I mean, it's a problem itself how to compute maximal eigenvalue of a set of matrices efficiently. So we use external libraries. And how to compute the optimal norm, and for that we use external libraries. Of course, I mean, the question is why it works at all. So we have a bunch of lemmas and theorems in our paper where we prove correctness of this approach. It's kind of, on a picture, it kind of looks simple, and it's simple in implementation, but we need to do some hard work in proving correctness. So this is the main theorem from our paper. It essentially says that this stretching factor measures the rate of, I mean, the stretching of the radius of the ball overestimate. So the theorem says that given a compact conservative enclosure for gradients, we can compute this lambda here is upper bound for Cauchy-Green stretching factor for all gradients in this set. Then the set of trajectories at time t1 starting from anywhere within this set of initial states is contained in a ball of radius lambda times initial radius, and the ball is in matrix M1, which comes from our algorithm. So a few words about implementation. So to compute gradient, we use CAPD library. So we use, at the moment, as I said, we have like a prototype implementation. So we just we use several libraries and communicate within them to compute eigenvalue bounds, we use some specialized intlab library to solve optimization problem for the semi-definite optimization to find positive definite matrix. Defining the norm, we use MATLAB packages, so we needed to implement kind of interface to communicate C++ with MATLAB. So the downside is kind of slow, but this is for the moment prototype implementation. And in fact, we could we found out that we could improve over existing approaches for some benchmark problems. So I list benchmarks here. So this is like acronym of a system of ODEs. B is like Brusselator, I is like inverse van der Pol, L3 is Lorentz. In brackets we give dimension. Right, so so you see in bold, so this is LRT, this is our implementation. This is, we compare with Flowstar, direct use of CPD. This is naive implementation of our algorithm. Doesn't matter. In bold, it's the best performance. And the metric is finite to initial volume of the rich set and average to initial volume of the rich set. And we could, for some systems, we could improve, as you see in this metric. For Lorentz, we couldn't improve, but this was not expected because Lorentz is like chaotic system and the state-of-the-art libraries for that. But for most of these systems here are stable in a sense that there's like a stable orbit, so we could improve it. Okay, let me stop here.
Questions? Can take a few questions while the next speaker is setting up.
So how tied is your analysis to the type of norm that you pick for your ball? Is it only applicable for L2 norm or any norm that you...
No. So the norm we choose is chosen in algorithm, and it changes from step to step. Yeah. And and what is your question?
Did you choose an L2 norm that is all your or all your states circles or ellipses, or do you
it's changing from step to step. Yeah. So there's like we have representation of a rich set, which is like a center and a radius and a matrix which define metric space. So the output is like at each step there's a radius, center, and metric space. Yeah, and it changes. So it's not the same for all steps, and it depends on the system also. Yeah.
Here, in view of the embedded optimizations that you run at every time step, it seems like the algorithm is hardly scalable as the time horizon grows.
Right. So this is at the moment we have like a prototype implementation. So I mean it's not really efficient. Yeah, I have to say. I mean it's not scalable. But I mean the improvement is in terms of diameters of the sets. Yeah. So we are working on a tool which will be kind of more scalable and more usable at the moment. So hopefully.
It's positively surprising that since you have to compute the maximum eigenvalue of a set of matrices in a set, so the spectral radius, you get results that are not very conservative because intuitively I would expect the opposite.
I mean, you would expect that...
that the rich sets will be very conservative.
but they are conservative.
Yeah, but less than what what flow star will give, it seems, right?
No. I mean, that's no. Our is on the left. LRT.
Indeed.
Yeah. So that's where we compute. In LRT, we compute eigenvalues, overestimate eigenvalues,
Indeed.
and it's better for those systems when it's in bold.
Indeed. Yeah. So
So
this is
maybe-
positively surprising. I would say.
Yeah.
Maybe we can take this conversation after the session. Yeah, let's thank the speaker again.